Hi, well we're back for the second part of our lecture on linear functions. Before, if you remember, in the first part we talked about the structure of linear functions, generalizing some things that we had looked at for arithmetic sequences. And so we looked at the structure of the table, the graph, and various forms of the equation, and talked about especially about this idea of the slope and generalized our formula for the slope. Today we're going to talk about direct variation and applications. So direct variation or direct proportion, the way we see that is just a different language for writing linear functions that go through the origin. So if you see the function of the form y equals mx, where m is the constant slope, and notice that this has a x and y intercept of 0. So this is essentially both the x-intercept form and the y-intercept form here, basically. So we notice that these go through the origin. Sometimes when you're using the language of direct variation, they use the letter k instead of m for the slope, for our constant of proportion, or constant of variation, or proportionality constant. So sometimes you'll see this said as y is proportional to x, or y is directly proportional to x, or y varies directly as x, or just y varies as x. So the directly is implied if it's not said explicitly. And so this is a language for generating this kind of a linear function. And so basically the output is just some constant number times the input. So it's a proportion, and of course the ratio of the output divided by input is that constant, is that slope. Okay. So notice that these functions include the origin 0, 0. So basically a 0 input gives you 0 output. 0 output comes from a 0 input. And so every time the input increases by 1, the output increases by m, but they both start at the same point with 0. So sort of a simplified version of a linear function, and it only goes through the origin. Now this language of saying y is proportional to x, or y varies as x, this is a language that some people will use, and especially scientists have a tendency to use a language like this. So let's look at an application of this. In a scale drawing, the length of the actual object is proportional to the length of its drawn representation. In a particular drawing, the scale is 1 to 50. Write a formula for the actual length, L, as a function of the drawn length, D. What is the width of a room that measures 40 centimeters in this drawing, and how long should the drawing be for a wall of length 10 meters? Go ahead and work this, and then come back when you're done. Press pause now. Well, notice since the room is the bigger one, the actual thing is the bigger one, and the drawing is smaller, the 1 goes with the drawing, the 50 goes with the real thing. So basically, if you have a 50 centimeter real object, you have a 1 centimeter drawing of it. Now, we asked for the length as a function of the actual length as a function of the drawn length. L is a function of D. So L of D is 50 times D. So there's the function. If we did the inverse function where we had little d equals, then it would be 1/50th of L. What's the width of the room that measures 40 centimeters on this drawing? Well, 40 centimeters is the D value, so this is just L of 40. 50 times 40 is 2,000, so the length is 2,000 centimeters. Or we might write that as 20 meters, because they're 100 centimeters per meter. How long should the drawing be for a wall of length 10 meters? So now we put 10 meters in for L. 10 meters equals 50 times D, divide by 50, and we get D is 1/5 of a meter, or 0.2 meters. If we did that in centimeters, that would be 20 centimeters. Alright, here's another example. The amount of gasoline a car uses on a trip is proportional to the length of the trip. It uses 20 gallons for a 300-mile trip. Write a formula for the length of the trip as a function of the amount of gasoline used. What is the proportionality constant, and interpret its meaning in the context. Be sure to include units. And how far can the car go on a tank of gas if the tank holds 25 gallons? Okay, press pause and work this now. Well, let's see. It's a direct proportion, so it's just D equals M It's like y equals m times x, or in this case d equals m times g, if g is the gallons of gasoline used and d is the distance traveled. Now the trouble is we don't know the slope m, but we can solve for that because we know a point on the curve, and so we can plug in 300 for d when we plug in 20 for g, and then solving for m by dividing both sides by 20, we get m is 15. So now we plug that back into our formula. D of g equals 15 times g. So now if we change d or g, the other one changes, but the 15 is fixed for this particular automobile. What is the proportionality constant? Well, that's 15, and that's the slope. And of course, that's going to be in, notice how we figured it out. We took the 300 miles and we divided it by 20 gallons. So the units are miles per gallon. In general, the slope is going to have is delta y over delta x, so it has y units over x units, or in this case delta d over delta g, so it's the change in distance over the change in gallons, so that's miles per gallon. And so that's the car's gas mileage. Sometimes it's written as MPG, miles per gallon. And when you buy a car, they'll have estimates of that posted on the car. How far can the car go on a tank of gas? If the tank holds 25 gallons, that's just going to be 25 in place of G for gallons. That's D of 25, so it's 15 times 25 is 375, and it is in miles. So that would be the range of the car for one particular tank. Okay, here's another application. The following table gives the position mile marker of an automobile on I-40 as a function of time t measured in hours since 8 o'clock a.m. Now notice this one goes through the point 012, not through 0, 0. Okay, so this is not a proportion, a direct proportion, but it is a linear function. Well, maybe it's a linear function. Let's see if it is or not. How would you know if this is a linear function? And if it is, what assumptions are we making here? And if it is a linear function, find the slope and interpret its meaning, and write the formula, and then compute these other things down here. Okay, go ahead and work this out now. Alright, the first one, this is linear, and now we know this because we figure the slope. So if we find the slope between the first 2 points, so the delta y over delta x, delta y or delta p is 146 minus 12, and delta x is 2 minus 0, or delta t in this case. And so delta p over delta t, or delta y over delta x, is the slope, and that turns out to be 67. And if you do it between the next two, between time t equals 2 and t equals 3, again we do 213 minus 146 for the numerator, that's delta y, or delta p. Delta x or delta t is 3 minus 2, and divide that out, work that out, do the subtractions, then the division, and you get 67. Likewise, the slope between the last two is 67, so the slope between any two of these points is 67. And so that slope is the rate of change, and of course that's a change in position measured in miles, mile markers, divided by change in time measured in hours, so that's miles per hour, which is its speed. So the slope is an average rate of change. In this case, the slope is the average speed. Now we can write the slope y-intercept formula. P of t equals mt plus p sub 0. Y equals mx plus y sub 0. So instead of y, we call it p of t. Instead of x, we call it t. The slope is, we just figured out, is 67. And the initial value is the p-value when t is 0, which we see from the table is 12. So the formula is p of t equals 67t plus 12. And you can check to make sure that all those things in the table check out, either using your calculator or do it by hand. What's the location of automobile at 1 o'clock? Well, first of all, we got to figure out what t is. T is the time measured in hours since 8 a.m. Okay, remember time goes up to 12 and then it starts over again, so 8 to 12 is 4 hours, and then from 12 to 1 is another hour, so t is actually 5 at this point. And so we just plug in 5 for t and work it out. 67 times 5 plus 12 is 347, so it's at mile marker 347. I should have answered this in a sentence here, but I ran out of room here, so I should say the location of the automobile at 1 o'clock p.m. is mile marker 347, assuming that they don't restart before then. Compute the time that the automobile reaches mile marker 237. So 237 is the p-value. So take the same equation and put in 237 for p, subtract 12, and then divide by 67, and we get t is approximately 3.3582 hours. So we want to figure out what time of day that is. We need to do this in hours and minutes. So there's 3 whole hours, and then you take the 0.3582 times 60 minutes per hour. The hours cancel, and that turns out to round off to 21 minutes. So that's 3 hours and 21 minutes plus 8 o'clock in the morning makes us 11:21 a.m. So if we were answering a sentence, we would say the automobile reaches mile marker 237 at 11:21 a.m. So this is an example of a linear function, and we were able to figure that out, that it was exactly linear by the table. Now, of course, what we're assuming here is that the pattern continues between these numbers and beyond these numbers. So we're saying basically that the speed is constant. So basically what we're saying is the car comes up here, sets its cruise control at a certain speed, it stays that speed, and it never adjusts up or down for any reason. Of course, that's really unrealistic, but it could be a close modeling. At least in terms of the average speed, it could stay the same. But what we're really assuming here is that it never changes, completely constant speed. Alright, here's another application. The cost of full-time tuition for a semester at a university was $2,100 in 2009, and at the same university there, $2,400 in 2011. Assume that the tuition is going up at a constant rate. What kind of function is this? How do you know? What assumptions are you making? What's the slope? Interpret its meaning in the context of the problem. Be sure to include units. Write a formula. Compute the tuition in 2012. And then when will the tuition first reach $3,000 per semester? You should be able to figure this out. Stop this now and work this out and come back when you're finished. Press pause now. Well, the fact that this is a constant rate of growth, that is exactly what makes it linear. Of course, in reality, this is probably only true for maybe for a few years that it went up by a constant amount. So the domain is probably limited here, but definitely limited. At a certain point, the university didn't exist if you go far enough back, and likely this formula only applies or models the situation well for a few years. But what we're doing is assuming that for the years that we're looking at, this formula will apply. So the slope is the average rate of change. We just use the delta y over delta x to find the slope. Delta y is the change in y's, and y's are the tuition. Okay, actually I use y for the input here instead of x. So normally where I put an x, I put a y for year, and used a t for the output. So we got t of y. So it's delta t over delta y instead of delta y over delta x. But anyway, it's a change in the output divided by change in the input. So that's $2,400 minus $2,100 is $300. Divided by, well, 2011 minus 2009 is 2 years. Work that out. That's $150 per year. So what this means is that the tuition is going up at a rate of $150 per year. So the formula then in point slope formula would be t of y equals 150 times parentheses y minus 2009 close parentheses plus 2100. You could have easily done this as t of y equals 150 times y minus 2011 close parentheses plus 2400. And of course, if you'd rather, you can distribute and combine like terms here to get this in a slope y-intercept form, or you could factor it out and make it a slope x-intercept form. So there are various forms we could do, but it was sort of natural to use the slope point form or point slope form because we were given a point and we could easily find the slope. Actually, we're given 2 points. So compute the tuition in 2012. I can just, it's t of 2012, put that in there. And actually I worked this one out step by step. The steps have a meaning here. So 2012 minus 2009 is 3. The 3 represents how many years have transpired since 2009. The 3 times 150 is 450. That's how much the tuition went up over those 3 years. The 2,100 was the initial tuition in 2009. So when you add those together, the total tuition is 2,550. So we put our answer in a sentence. The tuition at this particular college per semester in 2012 was $2,550. When will the tuition first reach $3,000 per semester? Well, that's 3,000 is placed in place of the t and solve for y. So we put the 3,000 in there, subtract 2,100 for both sides, and you get 900, which is the change in tuition from 2009 to whatever year this is going to be, where it reaches 3,000. Divide by 150, that's 6, and that's actually the number of years that it's going to take for that to happen. Add the 2009, you'll see which year it is. That's 2015. So if the pattern continues, tuition will first reach $3,000 per semester in 2015. Okay, how about another application? The temperature T is 72 degrees Fahrenheit at 2 o'clock p.m. and is dropping at a constant rate of 3 degrees per hour. What kind of function is this? How do you know? What assumptions are you making to reach this conclusion? What's the slope? Interpret its meaning. Find a formula. Compute the temperature at 2:30 p.m. and when will the temperature first reach 60? Very much like the last one. This time we're given a slope and an initial value. So see if you can work this one out yourself and come back and check it when you finish. Press pause now. Well, since we're assuming that the rate of change is constant, this is a linear function. That's exactly what linear functions are. So the slope is the average rate of change, and since the function is decreasing, the slope is negative. So the slope here is negative 3 degrees Fahrenheit per hour. So each hour the temperature is 3 degrees Fahrenheit less than the hour before. So write a formula for the function. If we let capital T be the temperature and little t be the time in hours past noon. By the way, notice that capital T and lowercase t are potentially two different variables in mathematics. So you can't really use those interchangeably. Now, if you find that confusing, you could have chosen different letters. But whatever letters you put in, you should probably say what they are. There was nothing in this. Well, I guess it did say temperature T, capital T. So it sort of told us to use capital T for temperature, but it didn't really tell us what to use for time. So you had a choice. I used T for time, lowercase t for time, but I could have used something else. But whatever you're going to use for your letters, you should identify what they are, what they stand for. So anyway, our formula is capital T of little t is negative 3, parentheses t minus 2 plus 72. That's a slope-intercept form. And t was the hours past noon, and so then I did it this way. You could have let maybe x be the hours past 2 o'clock. You can do it different ways. I picked noon because it'll be easier to figure out the time of day from this. So compute the temperature at 2:30 p.m. Now 2:30 p.m. is exactly halfway between 2 and 3, so that's a t value of 2.5 because it's exactly 2.5 hours after noon. So we just do t, capital T of 2.5, plug that in. 2.5 minus 2 is 0.5, so in other words, half an hour has elapsed since 2 o'clock p.m. Multiply by negative 3, that gives you negative 1.5. That's the amount of drop that you have in the, or change in the temperature, and we add that to our original 72, so that gives us 70.5. So that means the temperature at 2:30 p.m. was 70.5 degrees Fahrenheit. When will the temperature first reach 60 degrees Fahrenheit? You plug in the 60 in place of the capital T, the temperature, on the left side of the equation, and solve for little t, the time. Subtract 72 from both sides to get negative 12 equals negative 3 times t minus 2. Divide both sides by negative 3 to get 4 equals t minus 2. Add 2 to both sides to get t equals 6. The temperature will reach 60 degrees Fahrenheit at 6 o'clock p.m. So, after studying the material in this lecture, and the two lectures on this video, students should be able to do the following with and without the aid of technology. Describe the characteristics of linear functions present in the table, in the graph, and the slope y-intercept form of the equation, the slope x-intercept form of the equation, and the point-slope form of the equation. You should know all the characteristics of each of these different things. How do we see and how they relate to each other, to start with one and go to the other. So you should be able to produce each of the representations above for a linear function given any sufficient condition for determining the function. For example, just given 2 points, you should be able to figure out all of these things. Given a point and a slope, you should be able to figure them out. Giving a slope and an x-intercept or a slope and a y-intercept. So there's various different ways, and plus you should be able to look at a table and see if it's exactly linear or not. And of course solve applications using each of these techniques and understand what's meant by direct variation.